start then. So, um, so let me kind of back up a little bit and start with this point that I was trying to convey towards the end. So, I cannot kind of um, overemphasize the importance of the Fermi-Pasta-Ulam-Singo problem. And the reason why it is so is basically because uh, this problem has, if you will, thrown a massive talk about noise. This is the noisiest of things that have been dumped on it because um, people like, Fermi and Lam and Pasta, who were seen as real heavyweights in how deep their understanding was, they failed so miserably at a human level in um, engaging what outcome to expect, which clearly means something. And what it means is they were missing some kind of fundamental property of these systems. That's what it means. Although nobody says that, but that's my take on it. They miss some fundamental um, feature of the system. It's almost like going to the moon without expecting the moon to be Earth. Uh, it's almost like that, right? In other words, they were flying blind. That's basically what it boils down to. But they didn't know it, right? And that is so unexpected from people of that caliber. And so the suggestions that came, especially, for example, with regard to this paper, you can see this paper, right, that I discussed last time by Levy et al., where they kind of did, back in 1985, which were fairly early days of doing heavy duty dynamics computations. They did the study and they came up with the conclusion that below a certain system energy, total energy, uh, it is possible that the system never relaxes. Now, let's look at it from the lens of what you and I know from statistical mechanics. You and I know from statistical mechanics that phase transitions are very special. And the system being one phase versus the system being another phase, if there is a boundary, then there is usually some deep reason for that boundary. There's some collective physics that comes around. And that collective physics is what facilitates the phase transition. When water boils, for example, the whole water boils together. Everybody boils off until, at 100 degrees. It is not 101, it is not 99, it's 100 degrees. So it's a collective process. Everybody is conspiring to be at 100 degrees for it to keep boiling. And the energy supplied should be proportionate and all that, given the losses. So given that lens, given that background, the fact that you have a phase transition in a one-dimensional nonlinear model at a particular value of energy for which there is no obvious reason is shocking and confusing, to say the least. Why should that happen? There's no reason for that to happen that one can honestly foresee. So when this paper came out in 1985, it had a clear impact because these are very respectable people who had a result where they saw that the system goes to thermalization above this energy scale, but below this energy scale, there is something happening. So 30 years later, with much more advanced computing available much more readily, when Honorato and Vozella and Proment and Lvov wrote that Proceedings of National Academy paper, Route to Thermalization in the Alpha Fermi-Pastel system, which I had talked about in the last lecture, it was quite evident that the system does relax at all energies. So that energy cutoff scale that Livy et al. Had thought of, that they had sort of picked up from their data, turns out to be a red herring. That's not true, because no matter what happens, the system does relax back to equipartitioning, and the energy gets distributed among all the modes pretty uniformly. It's just that you wait longer and longer and longer, depending upon the amount of energy involved. If the amount of energy involved is smaller, then you wait even longer. So here you can see if the amount of energy is, for example, 8.48 10 to the minus 2, that's the black line here, whereas if the purple line is 5.66, then it relaxes much later. So you can clearly see that as the energy goes lower and lower and lower, the relaxation times increases. That's much more understandable. That's more physical. That makes sense. Now, the content of this paper, Tony, if you have a chance, I know you're very busy now with all the graduation issues coming up, but if you can, take a look at this Proceedings of National Academy paper, because the point of this paper is something which also is very exciting. And that is that we talk about two-particle interactions and energy exchange as a nice approximation with which we can mimic the physics of many particle systems. This paper, on the other hand, makes the case that very, very high order effects in particle-particle interactions actually enter into facilitating this relaxation. So in effect, it's something like not only interactions between two particles, but interactions between three particles, four particles, those little pieces that normally shouldn't even play a role. Even those guys, they begin to play a role, and they cannot be ignored. So that's really the content of this paper, which I did not want to get into because it is fairly technical. But it is these higher order interactions, in fact, I believe they take up to 8 orders of interaction, that turn out to be critical, that turn out to be essential in being able to model the relaxation process and get results as expected. Okay. Now, is this correct? Is the calculation correct? I don't believe we know. Does the calculation suggest that the system goes to equipartition anyway? The answer is yes. The calculation is correct to the extent it points in the right direction, but if the numbers gotten here are numerically the perfect numbers, we don't know. Unless you do a point-by-point comparison with the same kind of simulations and the same kind of setup and everything else. So that's also a caveat that we have to keep in mind. So the point is that the system does relax. And this is a very big deal. Why is it a big deal? Well, it is a big deal because you are saying I can take a mass spring chain. If it's fully harmonic, then this will, of course, never equilibrate unless the number of particles goes to infinity, because that's the only way you can have an infinite number of modes, which is the only way it can facilitate a true relaxation, because otherwise it will just give you a whole bunch of sinusoidal terms. So fundamentally, for relaxation to happen, the moment you turn nonlinearity on, even for a single spring, you have an infinite number of frequencies. So you have a two-particle system with a nonlinear spring, you still have an infinite number of frequencies. So the difference between linear and nonlinear is completely, you're in completely different universes, almost. And here, you have this weak nonlinearity, and the weak nonlinearity triggers you back to energy being uniformly shared, which we call thermalization. So in other words, Fermi's intuition was quite on the money. Fermi was correct. It did go to equilibrium. accepting they couldn't get it because it takes so damn long. And it took between 1955 and 2015 to go from there to here. At least somewhat convincingly. That's what it boils down to. So that's why this paper or these papers are so important. And that's why, to me, this is one of the most exciting and important and consequential things about learning to do nonlinear dynamics. Yes, Tony.
Oh, I see that time, it's like 10 to the 6, 10 to the 7 time. What is the units of these times?
Yeah, these are set with dimensionless units typically. So
Okay.
in other words, everything is typically set to one. If you look at the paper though.
Okay. Yeah, I found the paper, so I downloaded it. So I'll give it a read later.
Yeah, I don't think you will find any kind of CGS or SI units. I think they're just
Okay.
set up. And the way it is done is you set up the integration in such a way that the total energy is fixed. So the integration time scale,
Okay.
your time step rather, is fixed by what kind of a um, energy conservation tolerance you're getting. Um, for example, when we do calculations, energy conservation tolerance would be like 1 part in a billion. That's typical. 1 part in maybe 100 million to a billion. Okay, maybe more. We have gotten energy conservation tolerance of 1 part in 10 to the minus 11 also. So yeah, I mean, we get pretty good energy conservation when we do it correctly. But if energy conservation doesn't hold up right, you're almost certainly making an error in the dynamics. So if it drifts at third or fourth decimal place, it's not reliable. You're incurring quite a bit of error. So these are conserved energy systems, so therefore they can be monitored as to how long they have run, how accurately they have run. But there is no conventional unit per se to answer your question. Now, so let us now ask the question as to why it is so difficult to do this problem. The reason why it is so difficult to do this problem, in my opinion, based upon our research, to what degree it is acknowledged outside, I have my doubts. Most people don't do the way we do this problem. That's why I can answer to you. When you have strong springs and weakly nonlinear spring interactions stacked onto that, that weakly nonlinear effect takes a very, 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 very long time to manifest itself. In other words, it primarily manifests itself as a harmonic oscillator chain, which is why Fermi-Pascal result was the way it was, because the very weak effects were the ones that giving the recurrence, that were giving the super cycles and so on that they talked about. Very weak effects. Now, what happens if you had, for example, um, strongly nonlinear effects and weakly linear effects? Let's flip the problem. Nobody discusses it because this problem has really not been examined before we took on this problem many years ago now. So I'll give you a hint as to what happens and let you digest it. The hint is if you completely turn off or almost turn off the harmonic piece and make the nonlinear piece the main piece, you basically get a solitary wave. If you put a velocity perturbation on a particle, then you get a solitary wave in this problem. Completely different answer than harmonic oscillations. And that solitary wave will hit the boundaries and so on, and it will indeed relax and go to equipartitioning at very, very late times. But in the scheme of things plotted here in this figure 1, that will happen rather quickly, maybe by 10 to the 5, 10 to the 6, because it is strongly nonlinear. So weak nonlinearity is a very difficult regime. So Fermi, Pasta, Ulam, and Singhu took on what was the hardest regime of the problem. And they missed the solitary wave, because that is the signature hallmark of these systems. They did the whole problem in a way upside down in the context of difficulty. Now, why did we start sitting in Buffalo thinking about the strongly nonlinear problem? I'll tell you that story today, because that story leads to another problem, which is intrinsically nonlinear. It is just not strongly nonlinear. It is intrinsically nonlinear. There is no linear piece in it. Okay, so I cut my teeth on that problem. And then I realized the Fermi-Pascal problem looks at the whole difficult problem almost upside down. So before I go there, I want to quickly touch back to something that I was talking about, and that was this paper we wrote back in 2018. There's some message came. Okay. In this paper, we actually took the Fermi-Pascal-Ulam-Singhou problem, but instead of taking the alpha problem, which is the cubic nonlinearity problem, which is what we were talking about, although Fermi-Pascal-Ulam and Singhou attempted both. But the main piece of the story I was telling you right now about the work of Levy and about the work of Honorato et al., that's with the alpha problem. But we went to the beta problem. The beta problem is different in the sense that in the beta problem, the Hamiltonian is like this. So the quartic nature of the Hamiltonian is the one that is giving you the strong nonlinearity. And in this problem, we assumed, because of our intuitive advantages, that beta is much larger than alpha. So it is a strongly nonlinear regime. In fact, in here, figure A, it is an intrinsically nonlinear regime because all you see is a solitary wave. And the second wave is coming as a remnant energy after generating this being used up as a second wave. There may be other very super tiny waves here also. In fact, they all have the same width, but they may not have the same height. The width is fixed by this nonlinearity 4. I think there is some hump here, but anyway, that's not a big thing. I can discuss that later. It's also not very well understood as to why these multiple small bumps come. So as you now turn alpha on, so you see in the first case in A, alpha is 0.01. So alpha is super tiny. And the effect is not coming, at least here. But when alpha is a little bit bigger, like 0.03, you begin to observe the evolution of a super tiny oscillatory tail. This is kinetic energy, so you don't really see the up-down oscillation so much. But I don't know, Tony, if you can see, but there is something remarkable about it. What is remarkable is that the soliton is actually separate from this oscillatory tail. And this is the hallmark of strong nonlinearity also, because the soliton feature is coming from this quartic term. But the oscillatory tail feature is coming from both the terms. This oscillatory tail feature is coming from a combination of the harmonic term and the nonlinear term. So the oscillatory tail is not entirely linear. It is actually a bit of both. The oscillatory tail becomes more linear-like as you raise the alpha value. For example, when alpha is 0.05, you clearly see that the soliton and the oscillatory tail are beginning to merge. It's unmissable if a word like that exists. That's your figure C. And in figure D, both are married together. They're part and parcel of the same pie. How amazing that with slight change in alpha, the physics of the system undergoes such a dramatic change. I mean, this is mind-blowing to me. That a slight change in alpha is 0.01, beta is 1. So it's 1%, 2%, 3%, 5%. By the time alpha is 10%, you have a problem that almost looks harmonic. Yet it's not. So the beauty of the FPUT problem is because it's brilliant that Fermi, Pasteur, and Singu started at the most difficult end of the problem. And they got something out of it. I mean, if that is not amazing, I don't know what is. So instead of being critical of the fact that they couldn't figure out what was going on, I commend them. I just feel that it's only because it was Fermi and Ulam and people like that involved. They could make something out of that incredibly difficult regime of the problem anyway. Shouldn't have been possible. And I certainly couldn't have done it. Now comes the question, Tony, of how these two pieces, the solitary wave peak and the tail piece, what is the math behind them? What describes them? What functions allow us to capture them? And that is why I had quoted this paper by Katja Lindenberg and her postdocs. Nonlinear oscillators, they took an array of nonlinear oscillators. And they pointed out something very, very simple. They pointed out that the oscillatory piece, the displacement of particles involved in the oscillatory piece, can essentially be captured by an integral of this Bessel function. That was a big piece of insight, not unknown insight, but a big piece of insight nonetheless. That was, very clearly and understatedly described in that paper of Katja and her postdocs. Katja is a very well-known figure in the field. She's getting up there now. I think she turns 85 this year. But this is, whatever she does is brilliant. And this is one of the most brilliant things I have seen out of Katja's papers as to how she declares this result. Of course, she cites where it's from and all that. But what you glean from it is that if you now look at the velocity of the particles, it'll be a differentiation of this integral, which means that the particle velocity is a Bessel function. So when we wanted to look at our work, which is this stuff here, and construct a description of the difficult figures that we were seeing here, for example, in D and C and so on, we figured that the velocity of the tail piece must be described by a Bessel function. And that's your Bessel function here. And here I say, for example, how this mu and kappa and everybody is related. Kappa T, kappa is the time scale that comes with it. Alpha is this alpha. I don't know what kappa is without taking a look at Katja's work. I recall struggling between the kappa and the K. The K is a normal K. I think that is the kappa actually. We called it kappa, I don't know why. Anyway, so the point I'm trying to make is that oscillatory tail is basically coming out of this Bessel function. And you can see that the index of the Bessel function actually depends upon the I here. A Ti, for example, is mu over kappa. What is Ti? Ti is the mu where kappa is square root of 8 alpha, and the parameter mu determines the time Ti at which the leading edge of the wave reaches particle I by Ti approximately equal to mu over kappa. So it's like a time scale of the problem when the tail reaches a certain particle. You have to think about the tail happening dynamically. You gave it a push, and then this leading edge propagates followed by a tail. So you have a particle here. When will that particle feel the tail? When will the tail reach it? That's this time. So as we say here, let Ti1 be the time at which the kinetic energy of particle I reaches 0.1% of its max value, and let Ti2 be the time at which it reaches its first minimum. Then Ti is this much. So we define this Ti and so on. How to measure? These are very delicate measurements, so rather technical, not so important. But the important point is that the velocity is the Bessel function. The other important point is, so what's a solitary wave? How do we describe that guy? And this is where we had conjectured that let it be a function which is a set square function, because solitary waves are normally described by set square functions like a Gaussian almost. But now, instead of making it set square, let's say z, you make it a polynomial. But turned out that we didn't need more than the second term, the cubic term. Because if we had a fifth order term, it was actually decreasing our accuracy. So we tried everything and we kind of honed down on this form. And you can see that about 0.8 is linear and a little over 0.1 in this case is cubic. These are all fitted numbers. There's nothing fundamental about it. We took these two functions, the Bessel function and the set square function, and fitted it to the plots at different times and saw what works. So by trial and error, by iterative guessing, we came at this. And it works extremely well. How well? It works well up to, 8, 9 orders in magnitude in time. That's how well. Of course, now the problem is that if you ask for a general form of this A and B, we don't know. We just have some idea of it. So the reason why we were successful in doing this is A, because we knew that the solitary waves are there, and B, because we knew, as Katya showed us, that the Bessel function is there. And it was a matter of marrying the solitary wave feature and the Bessel function feature with just the right spices, so it worked all the way. And that's what we did. And this plot I had shown earlier, you might remember from Thursday, where I showed that our formula-based line, which I believe is the red line, yes, that is the red line. And the measured wave from the simulation, which is this dot dashed line, they fit very well. I mean, this is a fifth order derivative, and it's only at the turning points you begin to see some errors. That's good. Really remarkable that it works. But we had prior background in this. There was a solution I developed in 2001 that was along these lines. And I basically used that solution. I kind of tailored that solution to construct this solution because the physics is related. Now, what about the fact that whether these are solitons or they are solitary waves? We know that solitons pass through each other, just slow down as they cross each other and completely recover. Whereas solitary waves, as they pass each other, they scatter. They produce something, whatever that thing is. Answer is very clear. They are solitary waves. This is before collision, this is after collision. This guy is here, that guy is there, and here you see what happens. So you have this whole thing forming here that is creating scattered waves. These are solitary waves also. This is what I called a secondary solitary wave. It is now pretty well accepted in the literature that these are secondary solitary waves as special effects. This is velocity. So this is also a secondary anti-solitary wave. That means a solitary wave is like a compression pulse, and anti-solitary wave is like a dilation pulse. Okay. So if you have a particle between two particles in springs, so if you push this particle, this gets compressed, but the opposite side gets dilated, right? So therefore, when they form, there's a compression pulse and there is a dilation pulse. There's a solitary wave and an anti-solitary wave. I did not show here the details of these solitary, anti-solitary, anti-solitary, all these collisions. We have these calculations actually in that particular paper that I quoted, which was this paper here, actually has all these calculations reported. This was in Europhysics Letters 2018, quite a few years ago now. So anyway, but there is a very fascinating story behind this. You see, this is a proof that what Fermi imagined, system will go to equipartition, actually happens. Why? Well, because if you let this happen, for example, if you now put the system between two end walls, hard walls, one, let's say at one, let's say at some other n, then one can ask the question, what happens at very late times? Well, take a smaller system, in this case, a 100 particle system. In this 100 particle system, particle 75 here has been given a velocity perturbation and a solitary wave develops. This wave starts to spread. This is a low velocity perturbation. It's a high velocity perturbation. Low velocity perturbation may have some oscillatory features because it may have a harmonic term there in the Hamiltonian. Here the harmonic term won't play a role because it's a high velocity perturbation. You can see all these characters beginning to form. But if you see at late times, you see that every particle is dancing in the system. The system is on its way to equipartition or equilibrium, but right now it isn't. And it isn't in equipartition yet, even though the system has been run for very long times. Normally, one would expect that when a system has been run for such a long time, it'll go to equilibrium. Why will it go to equilibrium? Because all these tiny secondary waves are interacting with each other and all that. There are continuous collisions happening, and therefore everybody is scattering everybody. And ultimately, the system drives itself to this equipartition state. But that is not quite happening here yet. And this is a hallmark for the system. And this is also the reason why it takes that long to equilibrate. In this case, it's worse because the nonlinear piece is weak. In our case, nonlinear piece is not weak. But even then, it takes a very long time. So this is a remarkable feature of this problem that is not easily appreciated. And it is very important because this leads to quote unquote new physics. New physics is very hard to find in 21st century, not much new physics that we can easily find. This is new physics. So I'll come back to this problem, but let me add another layer now. Yes, Tony.
So the more nonlinear contribution you have, the faster it will approach an equilibrium.
Yes.
Yes. Okay. Because a completely linear problem would not approach equilibrium. It would just oscillate.
Yeah.
Okay. Okay.
And a very weakly nonlinear effect will
It would take
will
forever to
make
get
time
there.
scale very, very large. Yes.
Okay. Okay.
Um, that's very well stated. Yeah, you're totally right. So I'm now going to add this other layer, which is um, also mind-blowingly beautiful. And it's so counterintuitive. This is Al Sievers. Al Sievers is now retired. Al Sievers spent his life as a professor at Cornell Physics and big name, very, very big name. By the way, Katya did her PhD in physics in Cornell, and I believe she finished in late 1960s. And while she was a graduate student, I was told by both Katya and by Al that she worked in Al Sievers's lab for a while. So that's how senior Al is. Al is almost 90. Um, lives in Colorado now. But he's an interesting guy. So I had invited Al Sievers to give a talk in Buffalo on his work, and he immediately accepted. But the day he was going to come, there was a blizzard. So Al couldn't come. So I rescheduled it. And because Al was already in his 80s, I offered to Al that, if you'd like, I'll come over and pick you up from Ithaca and bring you back. Al said, Surajit, I love driving. Don't even worry. And sure enough, he was there. And Al came to my office, uh, looking like what he is looking like here, but with a big gun case in his hand, rifle case, big one. I didn't know it was a rifle case, but uh, he was amused, of course, that nobody ever stopped him. Um, and when Al was ready to give the talk, um, he brought the rifle case with him. So I knew he was up to something. So he took out this experiment that he had rigged up, uh, in which he had an actual rod, which could be essentially, placed in such a way that it stands between two legs, or rather four legs, on a table. The rod is like that. And this rod had oscillators that can go like this vertically. And each of those oscillators were connected by springs. So this is a very nonlinear system, but the fact that it could go around meant there was strong nonlinearity and harmonic springs at the least connecting the oscillators. And Al showed, while he was giving his talk quite casually, that by just letting one oscillator go at one end or somewhere, there was one particular random oscillator that picked up all the energy and kept on going forever, macroscopically in front of your eyes. While he was giving the talk, you could see that there was no sign of this stopping, almost in defiance of intuition and frictional effects and everything. The nonlinearity was so strong that all the energy concentrated in one particle spontaneously in the system. So this is the kind of character Al Sievers is. And this is one of his very famous papers. It's a long paper. It's a Reviews of Modern Physics paper. And these are they were his very steady collaborators, Sato and Hubbard. But this is his system. Okay, it's a very tiny system. It's a system, as you can see, he has sketched it here. It's a silicon nitride layer And he has this way of essentially carving out these micro cantilevers. So think, for example, of I don't have one here. Think of a hairbrush. Think of a comb. So this is basically a very tiny comb, right? You have all these cantilevers, and in this particular sample, he has two different sizes from what I can tell. But by doing the correct kind of etching, he could make one impurity. So imagine one of these is an impurity. In this case, it's like a diatomic atom. If you put in one impurity here and everybody else is the same size, it's like a single impurity problem. If you make all of them the same size, it's a monodispersed chain type problem. But each of these cantilevers, they give nonlinear oscillations. And this cantilever connections through this solid base is equivalent of spring connections. The math is not easy. So, don't have anything that I can use to demonstrate quickly. But let us say that I take this ruler here and I put some little rods and connect it nicely with the ruler. Then depending upon the actual shape of these little rods, whether they're perfectly rectangular, whether they have some funny shape, like pointy shape or broad on the other end or something fancy like that, the nature of the interaction between this rod and the next rod will be fixed. So study of interactions like these on cantilevers is a topic in applied mathematics in its own right, because you can almost make an enormous variety of extremely complex nonlinear systems using various forms of these and various forms of these tiny cantilevers. Al has done a very simple system in this case, which you can observe with very high precision, but there is a group led by a gentleman by the name of John Sader, I think Sader, in Australia. Sader is, if I'm not mistaken, Sader is a graduate or postdoc out of Caltech. So he has done a lot of work in the US also, but he's based in Australia. And Sader is one of the big experts, for example, in this field. He's an applied mathematician who constructs the Hamiltonians, if you will, for these various forms of cantilever systems. And they can make, for example, you want to mimic the interactions in a DNA molecule. It can be mapped onto one of these systems, let's say, if there are localized oscillations. And that is the kind of stuff that Sader does. I didn't know about his work until one of my former students was interviewed by Sader for a job. That's how I got to find out. And I was fascinated. Anyway, so coming back, I now want to tell you what Sievers did in the studies reported in this paper. Sievers essentially drove the system, meaning he drove the oscillations of these cantilevers in this system or a similar system. And this is actually, one of them is experiment, one of them is simulation. Experimental results for A through C. Oh, both are similar. One is a 248 element, the ones on the left, and these are 152 element arrays, and they are taken with a 1D CCD camera. The PZT driver, this is piezoelectric some driver, has a fixed frequency at the top of the optic branch. Running modes are produced. So basically it drives the system up to a point and then turns it off. So he has pumped energy into the system up to a point and turned it off. And then he wants to see where the energy winds up. Because each of these little things that you see here, I hope you can see them. You see this vertical, rather these horizontal lines? They're all cantilevers. These are the cantilevers, these tiny, tiny ones. The cantilever vibrations are being caught. Here they're sitting steady. It turns on a chirp. This chirp goes on until this white line, and then it turns the chirp off. So the excitation has been distributed to every cantilever here, starting here, ending here. Now the question is what happens to the energy? This is exactly like Sievert's rifle rack. The energy winds up in one or two cantilevers, and that's where almost everything is sitting, and much, much less everywhere else. Exactly the same example, but in a very, very different length scale and time scale. So this is not a Fermi-Pascal-Lamb-Single potential, but it's a very similar problem. You have harmonic interactions, but the on-site piece, there's an on-site piece, not a quartic term, but an on-site piece. This on-site piece is nonlinear. Each of these cantilevers are nonlinear oscillators. And it is these nonlinear oscillators that are interacting with each other with the body of the structure, with the base of the structure, bus bar of the structure, and that's what giving an effectively harmonic interaction. That's exactly similar to these rotating pendula that Al had brought connected by springs. So the models are the same. Exact same physics. I mean, this blew my mind. This blew my mind because it's the most non-intuitive thing I can imagine. Equipartition my foot. There is no equipartition. The whole thing goes on one guy. I mean, how counterintuitive is that? And look at what happens here. Here it picks up two of them. That also has happened. Here it also picks up two. A third one starts and fizzles out. A fourth one doesn't take off. The physics of these systems is not super well understood. In fact, one of my students, Rahul, when he was my student back in the mid 2010, so basically 2013, 14, that time scale, I asked Rahul to see if he could do this problem. And I asked Alexandra also, who was another student. She was very good. And they both literally killed themselves. And they were able to get pieces of this problem in our simulations, but we couldn't get it to stabilize quite as much, in part because our driving was a little bit different, but we couldn't get it to stabilize quite as much. We got it to stabilize quite a bit. I mean, I don't show that data here, but we came somewhat close, but not super close. Al had done good simulations also with his collaborators, and they see some pretty good results. So I wasn't super gung-ho about recovering it because I knew that we would be able to recover as simulations, but it will take a lot of time. And since he had already done it, I kind of said it's okay. By the way, these frequencies are high. They're in the kilohertz regime. So to get to Al's numbers, I saw that he was operating in a weakly nonlinear regime. I told him that, he said, I didn't realize when we were doing this experiment that we are actually operating in a weakly nonlinear regime, but he is. And that also makes it even more complicated. It's very oscillatory. But it's fascinatingly complex. So I turned my attention at the point because I kind of gave up on doing this problem in toto because I wanted to understand what are the structures of these localized oscillations. These localized oscillations had to have a structure. And they are not harmonic. They have lots and lots of interesting frequencies in them. So it's not like, so they're like an infinitely rich frequency spectrum. So it was very clear it's not a harmonic oscillation. It's a nonlinear oscillation. In fact, Al called them ILMs. In fact, if you see here, or if you see here, you see ILM. Intrinsic localized modes, he called them. I call them NLMs in my papers, nonlinear localized modes. Intrinsic because they come on their own. So this was a study we took on. And in this study, we actually took a Fermi-Pastor-Ulamb chain. What is the difference? The difference is that remember in Al's problem, in here, let's say, let me see if I can pull up something to write a little bit. Is it this one? No, it's this one, right? This one. So let's say I take, 1 second. I take this guy. So here I have V, the potential, as let's say Xi minus Xi plus 1. Hard to write with it. So one of them is a harmonic term. And the other one, this is 2 by the way. Other one is some kind of a, let's say, K, but Xi to the power 4. So it's not a bond, it's an on-site term. That's what's going on here. But since we knew that this problem is a little bit more manageable than the Fermi-Pastor-Ulamb problem, the goal was, let's go to the Fermi-Pastor-Ulamb problem here. So this is a pure Fermi-Pastor-Ulamb problem. Never mind these. These are basically, these parameters get you a Fermi-Pastor-Ulamb problem. But in this case, the harmonic term is turned off. So it's only quartic term. So the springs are only quartic springs. That's what I mean. No on-site term. So you have 100 particles connected by springs. And then we take particle 50 and 51 or 49 or 50 or something like that. I think it's bond 51. So bond 51, the way it is done, Tony, is the bond is squeezed. The initial condition is that the bond is squeezed. There's no velocity given. It's just a potential energy. All the energy of the system is concentrated in the potential energy of a single bond. And that single bond is bond 51. This is why in this color scale, you see that the energy is sitting in this bond. I can blow it up. In fact, because of the time scale, you can't see everything sitting in the single bond here, but that's what's happening. Say single bond. So the question was, what happens to the system? Does this energy sit on the bond forever? Does this energy leak out of the bond? And if it leaks out of the bond, how does it leak out of the bond? That was the question. Well, this turned out to be one of the problems that is so challenging that we haven't been able to solve it. However, we have managed to extract some important key insights from this very simple study. I mean, if you have the code, you just put the energy in the bond and see this happen. But this is a nonlinear localized mode that you're seeing. It's highly localized. It's highly nonlinear because there's no linear term. And the system is very slowly disintegrating. The first thing you see, in fact, it's impossible to miss, is that it emits these two lines. Now, here you're looking at position versus time data. So a line in a position versus time data gives you something moving at fixed velocity. What is moving at fixed velocity? This nonlinear localized mode emits two solitary waves. One here, symmetrically, as it should. But it is not instantaneous. You see that? It takes a range of space. I would say about 4 or 5 particles to actually come to the point of manufacturing a solitary wave. You are seeing the birth of a solitary wave from a localized excitation. How beautiful is that? And then you find that the system can't do whatever it wants. Once it births a solitary wave, it has to wait a while to birth the next solitary wave, which is this. But in the process, it pays a price because the excitation will have to disperse itself a little bit on the two sides. That's why I have these blue lines. See, blue lines here are like this, much lower energy, but the energy emitted here is also blue. So quite a bit of energy is being moved out of the central localized mode, and then it makes another solitary wave. After that, it can't make solitary waves using the same trick very easily, because what it does here is not moving along straight lines, so it's not a solitary wave. It's like your ship is beginning to sink, but it can't sink simply. The sinking is a complex process. So it starts to leak all over. Okay, it starts to leak all over. And then it begins to emit these structures, which are non-solitary waves. So we have seen solitary waves, we have seen harmonic oscillations, we have seen a combination of the two, and now we are seeing another species which carries a lot of energy, but it's neither here nor there because it doesn't move in a straight line like these guys. And in fact, what is funny is that you see it first leaks out this. This also leaks out something else. Then it leaks a lot out here, but it can't go out very far. It leaks more, then comes back. Same here. Then it leaks again comes back. What the hell is going on? How is it? How does a system do things like that? What is the physics? What is the dynamics? What is driving the system to make these very, very non-intuitive patterns? And it's almost always the case that after sufficiently long times, this localized mode actually breaks down into two branches permanently and then begins to form all kinds of solitary wave structures. But you know what? If you wait long enough, in many of these cases, they may also come back together to reform the localized mode. We have seen that too. Newtonian dynamics. Nothing fancy. Just a bond squeeze. Beautiful and extremely complex dynamics. So to understand this system, the following is what we did. Just to get you a little picture, because we don't have theoretical explanations at this level. So particle 50 is right here. This particle 50 is a part of that bond oscillation. And you can see that it has this rapid, unrelenting sinusoidal oscillations that it's executing. Very high frequency. The vertical scale is velocity of the particles. In this case, it's particle 50 velocity up and down as a function of time. So I don't know why this is here. But particle 49, which is this guy here, has a very, very different pattern. You see, particle 50 is moving so quickly that particle 49, which is adjacent to it, can't keep up with it. It's like if you are running back and forth in a room at, let's say, 5 miles an hour or 10 miles an hour. I can see you running back and forth. I want to run with you, but I can't run as fast as you can. So I'm like doing 3 miles an hour, maybe. So this is me doing 3 miles an hour. And this is the next guy doing maybe 1 mile an hour. But then we are slowly doing different things. For example, this guy's range changes up and down, the amplitude changes. So the amplitude begins to modulate. Even the patterns begin to modulate. And the third particle, which is particle 48, starts out almost random, unable to follow, then starts to rhythm in and does what it can. But particle 47 is super slow because the energy transference from here to here and from here to here and from here to here takes time. So this picks up energy much later, but initially when it starts out, it really can't do all that much. And particle 46, by the time, I think it's 6, is it? Yeah. By the time it begins to move, it is so slow that there is zero chance of it getting any piece of the localized oscillation. So it just gets a single bump. This is called modulation instability. So the single bump essentially matures into a very low energy solitary wave. So it is the mismatch that creates this guy. You just saw the birth of this guy because this guy is, this is the solitary wave. We couldn't do more because it's not only is it a lot of data, but you also have to see that even for velocity, we have gone down in velocity by 3 to 4 orders of magnitude, right? 3 times or 4 times 10 to the minus 1, and this is 2 times 10 to the minus 4, and this is 8 times 10 to the minus 5. So certainly 3 to 4 orders of magnitude almost is a drop in the velocity. They're moving very slowly compared to these guys. So this is the physics of this system. This is what nonlinearity brings, which is so intrinsically counterintuitive to what we know. Now, so what do you take out of it? Well, what we take out of it is that these systems primarily likes to make two things. If it can move energy, it likes to make solitary waves. The nonlinearity gives us that. If it cannot move energy because it has too much energy at a small spot, then it likes to make this nonlinear or intrinsic localized modes. That's what we have learned. If it has too much energy in one place, it cannot move it. Now, let me remind you there's something called the virial theorem. We've talked about it a few times. What is the point of the virial theorem? The point of the virial theorem is you give a system energy E, and the Hamiltonian, in particular, the potential part of the Hamiltonian, obviously bounces this energy between the kinetic and potential parts as the system evolves in time. So what is the time averaged portion of the energy that is going to potential energy? And what is the time averaged part of the energy that's going to kinetic energy? So that's the virial theorem. Virial theorem's job is to tell you if you give it energy E, how much of it will be kinetic and how much of it would be potential. In a nonlinear system with quartic potential, one can very easily show that 2/3 of the energy will be kinetic and 1/3 will be potential. In a harmonic system, it's half and half. Both are quadratic. In a nonlinear system, it is more kinetic, less potential. In this case, 2/3 is kinetic, 1/3 is potential. So now go back and see that in this system, we have put 100% of the energy in potential because that's sitting in the bond, 51 bond. 100%. That bond is not going anywhere. So you have essentially taken the system far, 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 far out of whack compared to what it needs, which is 1/3 potential, 2/3 kinetic. So this system is in a very uncomfortable state where its Hamiltonian is asking it to make 2/3 of the energy kinetic. It's got to move the energy. If it wants to move the energy, it has to do something, and one of them is making solitary waves. And that is exactly the reason why it starts off trying to make solitary waves. Very simple. There's no other choice. So, bottom line then is that this system is essentially trying to satisfy the virial theorem, and it takes a long time because it has to arrange for the dynamics to obey Newtonian laws and satisfy the virial theorem, if you will, and manage what's going to come out. But those are the laws that fix how its dynamics should proceed. So, so now you know that virial theorem is involved. You know that energy moving is typically done with a combination of solitary waves or solitons and harmonic or combination of harmonic and nonlinear waves, which are the tail parts. And you also know that if too much energy ends up in a bond, that will make localized modes. We know that. So let us go back to Fermi-Pastor-Ulam again and try to raise the question as to where does this solitary wave come from? Because the solitary wave in the Fermi-Pastor-Ulam-Singu system must be somehow buried in the potential itself. There's no other choice. So I want to point out this paper by Mason, Porter, and Zabusky of original Zabusky and Kruskal. Bambi Hu was a professor at Houston. He has passed away actually. And David Campbell, who's from Boston University, who is very well known for his works in the field. So they wrote this paper in Physics Today, and this particular one is an American scientist. They wrote a few papers some years ago now. If you can find it, I think it's freely available. It's fun to read. I'd encourage that you look into it. But I want to take you to the main point here, where Zabusky and Kruskal in 1965, 10 years after the work of Fermi, Pastor, Ulam, and Singu, pointed out that there are solitons in this system. So this was, at the time, an earth-shatteringly important observation, because this was missing in the study of Fermi, Pastor, Ulam, and Singu. By the way, Fermi wrote a paper in 1923, I think. This was a paper written in German. So I had used AI to translate it from German to English. And so I have an English copy of that paper. I'll be happy to share it with you. You have to find the copy. probably can share it with you right away. Let me see.
Use the restroom real quick, Professor.
Go ahead.
Thanks.
Yeah, no problem. Oh, you're back. I found the paper. Let me see if I can. Not a very simple paper, but uh, let me email it to while I have it. Oh, it's so difficult to find things when you have the Zoom going on. File, message, file. Oh, what happened? Running pretty low on time, I guess. Oh, stupid thing I'm doing. Okay, I just sent to you. Basically, the reason why I sent you the paper is because here Fermi argues that you know a normal mechanical system should go to some form of equilibrium. It's some kind of an ergodic system. Okay. Okay. All right. So let's finish up. But I want to just show. So the reason why I sent that paper is because Fermi himself expected ergodicity to happen, right? And that was the reason why. That was the background work he had done, that 1923 paper. So the point here I'm trying to make is Zabusky and Kruskal showed, as I told you guys earlier, that there is a connection between the Korteweg-de Vries equation and the Fermi-Pasta-Ulam alpha problem. And the way it works is that this is the Fermi-Pasta-Ulam alpha problem Hamiltonian. Then you write the equations of motion in this form in equation 2 here. And then you make a continuum approximation of the equations of motion of the first term on the right and the second term on the right. By the way, keep in mind that this Rj variable is a Bond variable. It's not a
Mhm.
site variable. It's a Bond variable. And for a Bond variable, the solution, if it's a solitary wave or a soliton, it becomes a set square because the bond indeed increases and decreases or goes down and goes up, which is a set square form. For a single particle, that's not so. For a single particle, it just gets pushed. It's a little different physics. It's a tan hyperbolic function. In the other case, it's a set square function. So anyway, so if you put this first term and the second term in continuum form, you have this feature coming in. And these two features now, if you put it together, you first have to uh, assume that there is a propagating wave, and therefore there is a co-moving frame. So your effective variable doesn't have to be x and t, but x minus ct. So it's one variable, c. And then you define this modified time variable tau, which is epsilon t, and this epsilon basically maps the u. U is this guy. U is this guy here, the bond variable. In continuum format, it's u. It maps the u to a phi, okay, with this epsilon. So then the del del x becomes del del c, del del t also becomes, one piece of it becomes del del c, and one piece of it becomes del del tau. So the c variable takes on a piece of x and a piece of t, and then there is a tau variable also. Now it turns out that you can rewrite that equation that we had into these formats. And by doing one integration on this, you can essentially bring it down to this format, and then you can further bring it down to standard KdV format. So this is the sort of nuts and bolts as to why the alpha problem can be mapped to a KdV problem. The beta problem cannot be mapped because the beta problem has much stronger nonlinearity. KdV doesn't work for it. That's one point I wanted to make before I finish. And this problem can basically be solved. You can actually solve it directly also. You don't have to use inverse scattering transform. You can do by direct integration. So I've kind of put it in here. And this gives you the KdV soliton, which is a set square function. All of these are more often than not set square functions. It's not God-given, it has to be set square. In fact, people have tried to see if there are Gaussian forms, if there are logarithmic forms. In fact, the conjecture is that the Gaussian form of a soliton may come from a logarithmic form of a potential. I read an interesting paper like that. So, but most of them that I have seen, regular guys, are the set square form. And this is a picture of an actual soliton. This appeared in a physical review latest paper, of which I actually was one of the referees. It's a very beautiful paper. And here you see it's a canal, which of course is not very deep, but very long. And here is a soliton, and here are people trying to go along the thing. And it's a typical KdV soliton. And this is a typical KdV multi-soliton, where you have, these are all individual solitons. So KdV not only accommodates a single soliton solution, it also accommodates two soliton solution and to n soliton solution. The thing about these nonlinear equations, Tony, is that the solutions are not unique. You can have one solution, but that does not mean that's the only solution. The same equation may support many, many solutions. And this is an example where you have a multi-soliton that's happening in an otherwise clean KdV problem in a canal. So with that, let me close here today, because now that I have told you about the weak nonlinearity and the mapping of the weak nonlinearity to the KdV problem, and that it gives you a soliton, the fact that you have these nonlinear localized modes, the fact that these nonlinear localized modes are most likely unstable because of the virial theorem, as we see, they also create solitons. I've tried to hopefully impress that whenever these nonlinear many-body equations come, there is a pretty strong possibility that if the energy has to be moved, solitons have to be the bearers of it. Just like if you have vibration in a harmonic system, the phonons have to be the bearer. So it's like a one-to-one almost thing between these two. So let me close here. I have a very, very interesting story in store on Thursday, where I'll take you to the intrinsically nonlinear problem and what happens there. And then you'll see how it fits the Fermi Pasta Ulam and all these things we have done. So let's close, and I'll see you Thursday. Thursday also, we might start a bit early because I think there is something going on. And I think there's a talk going on. I want to go there. All right, we stop recording.